So the problem stay open for a few years. And then Huffman comes along. Okay? Huffman code, so Shannon Fano published their algorithms in 1949, 1 year after the entropy publications. And then Huffman code is being published in 1952. And unlike Shannon Fano, it's a bottom-up algorithm. So you start with the lower probability symbols and you work your way up. Okay? And actually there's a, now Huffman code is very popular in practice. All of the JPEG images that you see on the web today, all the DVDs, movies that you watch every day, all the MP3 music in your iPod that you listen to every day has Huffman code in there. Okay? Which is an extremely strong statement, right? Without Huffman code, this is a tremendous application in practice. Now there's a very interesting story about Huffman code. Huffman is a student in Fano's course, information theory course at MIT, and Fano assigned this optimal code design as a homework problem. Okay, so Huffman 2 weeks later he turned in his solution and told his professors that this problem is actually very difficult to do. and Fano was so surprised to find out that, wait, you actually solved it? So, and he said yes, he showed the proof, and then he wrote a paper. Okay, so sometimes professors can be quite mean, right? Now, the encoding and decoding algorithm is actually very easy, and it's best to illustrate through a simple example or represent as a tree. Okay, so you start at the root of the tree, and everywhere you go, you either assign 1 or 0, depends on the left branch or the right branch. Okay, and these are the nodes. At the end of the nodes, those are Huffman code. Okay, so instead of going through the slides, I'm going to do the example because it's easier to understand. Okay, so I take exactly the same example as I had before with Shannon Fano, and we're going to try to do Huffman instead. Okay, so bottom-up algorithm means I'm going to try to combine these two guys into a newer symbol. Okay, so I can always do that, right? So whenever I see D and E, I combine them into a super symbols. Okay, I maybe label them DE, and then resort the table. So now I only have 4 symbols instead of 5 because I combined them into 1 already. And the joint probability of occurring is 0.31, right? So when I sort the list, DE comes up here and BC comes down here. Okay? I always put the more likely symbols upstairs. Okay? And then the next step, I'm going to do the same thing. Okay? I'm going to combine BC together and assign 1 to B, 0 to C. Okay? And then resort the table. So 0.17 plus 0.17 give you 0.34. Okay, so it will be above DE now. So the new list will become A, B, C, D, E, like this. Okay? And then I combine B, C, D, E together into another symbol. Big one, right? And then finally I get here. Okay. When I get here, I make my last assignment, okay, and then start to work backwards to construct the tree. Okay? So I start at the root, okay? Start the root, and then if it's 0, it's A. If it's 1, it's all these guys. Okay? 1, then it's all these guys. Now, I'm finished with A. There's nothing more that I can do on the right hand side. But on the left hand side, I have B, C, D, E to worry about. So I go up here, I say right. I say if you go left, then it's B, C. If you go right, then it's B, E. Okay? So if I go left, then it's B, C. I go right, then it's D, E. Okay? Are we done? Not yet, because I still have super symbols, right? Okay, so next step is to resolve B and C. And the other step is to resolve D and E. And I'm done. Okay? Now, I can construct the table. I read the table from the tree. Okay? If it's 0, it's A. If it's how do I get B? I will have to go 1 step, 2 step, 3 steps. So it's 1, 1, 1. How do I get C? I go 1, 1, 0. I get D when I go 1, 0, 1. And I get E when I go 1, 0, 0. Okay. How do we represent the prefix information in the string? What does it mean by violating the prefix condition? Prefix? Is this a prefix? This is a prefix of D and E, right? Because you have to pass through it to get to D and E. So you can never assign the intermediate node as a code. You have to assign the leaves. See? I never have anything that go through A. I never have anything that go through E, D, C, or B. Otherwise, I will violate the prefix condition. So I always assign, automatically you can see that Huffman code based on this construction will never violate the prefix code. Okay? Because we always assign the symbols at the leaves of the tree. We never take the intermediate node. Okay? So this code gives you roughly 2.30 bits per symbol. Now, comparing to the one before, it's 2.31, right? So obviously, this is slightly better. Now, you might say that, oh, 0.01 bits, who cares? Okay? But in practice, you are not transmitting 1 bit. You're transmitting billions and millions of bits. So these actually makes a difference. Okay? It actually makes a difference in practice. So this is, and obviously, as engineer, we want to use the optimal code. We don't want to use something that's suboptimal, right? Unless we have to. So this is certainly a better code to use than Shannon Fano. And comparing to entropy, obviously we still have some way to go, right? We're not as close to 2.23 as we want. So it turns out that there's something else that can do slightly better than Huffman, and that's called arithmetic coding. Okay? Now, Huffman is only optimal when you have cases like this. Okay? When you have cases like this, when the probability of occurrence of the symbols turns out to be power of 2. Okay? So this is 2 to the minus 1, this is 2 to the minus 3, right? These are power of 2. In cases like this, it's quite easy to show that Huffman always delivers entropy. Okay? Now let's take a look at this very simple example and work out the Huffman codes. Okay? Combine these two, assign, combine these two, assign, combine these two, assign, combine these two, assign, and then construct a tree. Okay? When you construct a tree, table Huffman codes look like this. 0 for A, 1, 0 for B, 1, 1, 0 for C, 1, 1, 1, 1, 1, 1, 0 for D, 1, 1, 1, 1 for E. In this case, you can see that the tree is nice. It's full, it seems to have very regular structure. Okay, and in this case, when we compute the average code word length, you will come up to 1.875 bits per symbol. And if you apply the entropy formula to the source, you will come up 1.875 as well. So in this case, it's actually matched the entropy, which shows that this is the optimal code that we can ever do for the source. Okay. Unfortunately, for cases like before, in the previous slide, we don't have probabilities that behaving nicely that 1/2 one, right? We have 0.35, 0.17. They're not power of 2. And in that case, there exists codes that do better than Huffman. Okay? Now, so Huffman's shortcomings is number one, it's difficult to make it adaptive to data changes. Okay, when your data change, so the frequencies, behavior change, Huffman codes is a very